Welcome to my YouTube channel Mechanical Magic Mechanical Learning Tutorials. So in this video I am talking about simple derivation and simple discussion onto a diesel cycles, or you can say constant pressure heat addition cycle. So basically this concept was discovered by Dr. Rudolph Diesel. So let us see onto a PV diagram for diesel cycle. So x-axis that will be a volume, y-axis that will be representing as a pressure. So at the beginning, from state number 1 to 2, so 1 having a volume V1 and that will be representing as a adiabatic compression process. So here for the adiabatic process, PV raised to gamma equal to constant. So in that case, from 1 to 2 state, that will be our adiabatic compression of air. So the pressure and temperature is being increased. So here from the state number 1, or you can say point number 1, that will be having a P1 pressure and that will be the lower pressure. So by the adiabatic compression process, that will be increasing up to the P2 temperature. So pressure and temperature that will be increasing in the case of adiabatic compression process. After adiabatic compression, and that will be the process 1 to 2, after reaching a P2 pressure, or you can say T2 temperature, then that will be having a constant pressure heat addition process. So P2 that will be equal to P3. So up to the point number 3, that will be done onto the constant pressure heat addition process. So volume and temperature is being increased. So from here, just you can see 2 to 3 process, that will be the constant pressure process. So during that, Q amount of heat supplied to the cycle. So that will be Qs, or you can say heat addition. So M, that will be the mass of an air which will be constant during the cycle. Cp, specific heat at constant pressure. So that's why Cp over here. And a temperature difference, that means T3 minus T2. So that will be the equation number 1. And during that constant pressure cycle, or you can say constant pressure process, V3 divided by V2, that will be representing as a cutoff ratio for an diesel cycle. So after constant pressure cycle, or you can say up to the 3 point, then that will be the adiabatic expansion process. So during the process 3 to 4, adiabatic expansion in this process. So during that will be pressure is being reduced. So here P4. So during that expansion, pressure is being reduced. Then after 4 point, that will be once again constant volume heat rejection process. So during that 4 to 1 process, Q amount of heat that will be rejected by the cycle or the systems. So at constant volume, or you can say constant volume heat rejection process. So here V1 that will be equal to V4. That will be the important term. So pressure and temperature of air that will be decreasing up to the initial condition, or you can say initial value. So in that manner, this diesel cycle is being worked. So from the 4 to 1 process, or you can say constant volume heat rejection, so that will be representing as a QR, that will be the rejected heat of M mass at specific heat at constant volume, and the temperature difference that will be from 4 to 1 process, so T4 minus T1. So that will be representing as equation number 2. So now I am interested to deriving a efficiency of diesel cycle. So basically efficiency, that will be net work done or you can say W net, that will be equal to heat supplied minus heat rejected. So in simple way, QS minus QR, W net. And one more relations, it will be here. So here air standard efficiency because air is used as a working substance, so that will be called as a air standard efficiency, net work done divided by heat supply. So from here just put the value over here. So net work done QS minus QR divided by QS. So from here just put the value from 1 and 2. So that will be MQS means constant pressure heat addition. So CP T3 minus T2 minus heat rejected, that will be MCV T4 minus T1 divided by heat supply. So that will be MCP T3 minus T2 over here. So from here just we will see 1 minus T4 minus T1 divided by CP into T3 minus T2. So from here and that CV, it will be like this. So CP upon CV, that will be representing as a gamma, we already know. So finally you will get 1 minus T4 minus T1 upon gamma T3 minus T2. So that will be the air standard efficiency. Compression ratio, that will be representing as R V1 upon V2, and cutoff ratio, that will be representing as rho V3 upon V2. And one more, expansion ratio, that will be V4 upon V3, so divided by V2 over here, so V4 upon V2 and V3 upon V2. So that will be nothing but our compression ratio, because V1 that should be equal to V4 from the PV diagram. You can see onto the diagram V1 equal to V4, because V4 to 1 that will be constant volume cycle, and V3 by V2 that will be representing as a cutoff ratio, right? So that will be all the important relations. Now considering for the process, you can see onto the diagram 1 to 2 that will be adiabatic compression cycle. So from the relation of the temperature and volume, T2 upon T1 that should be equal to V1 upon V2 raised to gamma minus 1. So V1 upon V2 that will be representing as a R. So R raised to gamma minus 1. So finally you will get from the 1 to 2 process, or you can say adiabatic compression process, T2 equal to T1 into R raised to gamma minus 1, and that will be representing as a equation number A. Now from process 2 to 3, you can see from the PV diagram, and that will be constant pressure heat addition. So from P1, or you can say over here P2 V2 divided by T2 that will be equal to P3 V3 upon T3. But constant pressure process heat addition, so P2 equal to P3. So you will get over here, and that will be T3 equal to T2 into V3 upon V2 from a constant pressure. So just you can see over here, in that case so T3 equal to T2 into V3 upon V2. So just put the value from previous one, and that will be T2 over here. So from equation A, T3 equal to, so we put the value of T2 over here, so that will be T1 R raised to gamma minus 1 into V3 upon V2. So that will be nothing but our cutoff ratio. So that will be the important relation of the T3 and T2. Now once again, from the process 3 to 4, process 3 to 4, and that will be adiabatic expansion process. So from that, T4 upon T3, that should be equal to V3 upon V4 raised to gamma minus 1. But we already know V4 upon V3, that will be from here R upon rho. That will be the cutoff ratio. So just put the value reverse minus 1. So T4 into T3. So just you can see by substituting value of T3 from equation B. So you will get T4, that should be equal to T3. So here T1 R raised to gamma minus 1 into cutoff ratio, and that will be gamma minus 1 upon R raised to gamma minus 1. So finally you will get, by simplify the equation, T4, that will be equal to cutoff ratio raised to gamma into T1. So by substituting the value of T2, T3 and T4. So just you can use these relations, 1 minus 1 upon gamma, and that will be T1 divided by T1 cutoff ratio R raised to gamma minus 1 minus T1 R raised to gamma minus 1 into the efficiency equations. So finally you will get the efficiency, that should be equal to 1 minus 1 upon R raised to gamma minus 1 into cutoff ratio raised to gamma. T1 common and cancel out, so here 1, and that will be into gamma into cutoff ratio minus 1. So that will be the final equations, you can say equation number C. So that will be representing as a efficiency of an diesel cycle. So just you can see that will be only depends upon compression ratio, specific heat, and cut off ratio. So basically in that diesel cycles, cut-off ratio that should be always greater than N1, and a value of gamma that will be 1.4 for the air. So in the case of the efficiency of an diesel cycle, always less than an Otto cycles for the same compression ratio because of that will be only depends upon the compression ratio. So thank you very much. If you like it, then subscribe and share. Mechanical Magic, Mechanical Learning Tutorials.